Okay, so hi everyone. Today I am going to talk about problems. I started in Div 1, but I performed very poorly. So, yeah, I no solution to problem C because I managed to solve it. I was also thinking during those 5 minutes or something on problems A and B, and right now I know solution to div 2A and I don't know about div 2B, but yeah, maybe I will try to live solve it. But we'll start from problem A, then go to problem C, and then I will try to live solve problem B. Yeah, I hope that next time someone better will do this stream. I don't know, cause yeah, I perform very poorly. Okay, but okay. So basically, in problem A, we are given a sequence of numbers and a number k. In this example, k would be equal to 3, and in one action we can choose k numbers with the same value, delete all of them, so go like to 1 1, and well, add some number to a sequence. We need to add some number to sequence, I think. Or are we just given an option? Oh, we need to exchange them for k minus 1 cards. Well, that doesn't change anything in the solution. So we need to exchange them for some k minus 1 cards, I would say. I would do something like this. And then we can exchange those cards to, well, wait, exchange these cards for k. Okay. And I would, well, change those cards to let's say one. Yeah, I will do something like this, and the answer would be 2, because we want to give the shortest sequence that we can get, right? And the answer is 2. So, well, the solution is to look at the array of counts. And what I mean, we'll count the number of occurrences of every element. So here it would look like this. We have 2 1s and 3 4s. But, well, we don't care about this value here, right? So we can just compress our array to 2 3. And, well, we know that in one operation, we can subtract 3 from one of the values and add 2 to some other value. Or to the same value, I think. Right? Yeah. Yes. So, well, I don't know if it works because I haven't proved it, but I think we can wait. Yeah, you can simulate the process, but you don't know how to pick the cards that you add, right? Really? Someone said on the chat that answer is always k minus 1 if we can start with any pair, else it's an. Yeah, you're probably right. Cause Wait, really? You're sure? If you would sort those counts, then... Well, I don't know how to solve it. It's kinda bad to don't know how to solve problem A from div2. But... if it is greater than k, then bring it to k. Then add k minus 1. Oh yeah, maybe it works, I don't know. Maybe we can look at the tutorial. Yeah, it's easy to prove. Yeah, so basically, if at the beginning each count from x is smaller than 3, then we can't make a move, so answer is n. And if at the beginning we have some count from x greater than 3, then what we can do? We know that we can always make our sum smaller by 1. How to do it? Well, the algorithm is as follows. Well, we can subtract 3 from the greatest count and then add 2 to whatever count is greater than 0. And we know that we always will have such count if, well, if sum is greater or equal k or something. Yeah. It's greater than k. So yeah, we can always get answer k minus 1. So I will say it once again. If we have some count that is at least 3, then the answer is k minus 1, and otherwise, if all the counts are smaller than 2, then the answer is n, because you can't make a move. So now to problem B. I will also look for the editorial because I don't know how to solve it. Yeah. In some cases. Okay, I understand. So problem B. In problem B, we are given a rectangle and every square is either colored black. I don't know, maybe I will draw it smaller. So every square is either colored black and any other square is colored white, right? So in one operation we can choose some submatrix such that one pairs of corners of this submatrix are the same, right? We see that we have, and color it all on the color of those corners, right? So we can choose some submatrix such that its rows are black, its corners are black, and then color it all black. And or we can choose some submatrix like, let's say this, some subrectangle, sorry, and well, or maybe like this, and we see that both this corner and this corner are white, so we could color it all white, right? We could color it all white. Okay, well, so the good thing to do in this task is we want to look at the, well, corners, right? And we know that if two like opposite corners have the same color, so for example like this, or well, like this here, those two are white, then we can just choose a whole grid. And well, so if two of the opposite corners are the same, then we choose the whole grid. Otherwise, we have something like this, right? Or some. Otherwise, we have something like this, or some, rotation of this. But we always want to rotate it such that it will look like this, right? Because rotations doesn't change anything in this task. So we always want to rotate our grid to get something like this. And well, if we have something white here, let's say in the first row, if we have something white here, let's say that, well, we have, for example, this square is white, then what we can do, in first operation we can do something like this, getting this corner white, and then, well, we have two opposite white corners, so that's our grid that can be colored in all white, right? And well, it's the same if in this row we have something black. Then we can just pick, let's say, something like this, color it all black, and well, this one is now black too. So once again, we have two opposite corners with the different colors. So, well, in either of these cases we see out yes. But let's say now that all the things here are black and all the things here are white. So, here we have this part of the grid. So, now we can show that well, now we can show that there is no way to change the colors of the corners, right? Because, well, we know that if we have some submatrix such that it will be symmetrical all the cases. If we have some submatrix such that it contains one of the corners, let's say this corner, then, well, it will look something like this, and it will go up here. So we know that two of the corners are black, right? Two of those corners. So no matter what we pick here and here, it will always, like, well, there can be like two black here, but we can't change the color of this, because even if both of those here are white, then, well, they are different than those corners here. I hope you understand. So basically, if two of the opposite corners in the grid given on input are the same, then we see out yes. If then we rotate our grid to always look like this, right? We rotate our grid such that well, black corners are here and white corners are here. And now we have shown that if there is some white square here or a black square here, then the answer is yes. Otherwise we have something like this and the answer is no. Okay. I hope that everyone understands. It's not really hard. So now to problem C, the only problem that I managed to solve on the contest. Well, in this problem, problem C, in this problem we are given a sequence, and in one move we can, let's say that the sequence is sorted. If it's not sorted, then we can sort it, because it will be nicer to think about sorted sequence. So let's say here or here, 2, 2. It's a sequence of piles. So in one move, a player chooses some number x such that x is smaller than all of the piles, right? And the player subtract x from all of the piles. So if I would choose x equal to 2, then I would have something like this from all the non-zero piles. And well, the player is unable to make a move when all of the piles are equal to 0. And we want to say if both players play optimally, who wins, right? Okay. So, well, this is kind of standard. There is like a standard game called, I think, Champ or something. Champ game. Wait, maybe it's written differently. It's like chocolate game. I don't know. Yeah, it doesn't show here, but it's like standard game theory thing. So basically, what we can show. Let's say that we make some move such that it's smaller than the first number, right? We make the move such that it's smaller than the smallest number. So let's say that we make a move equal to 1 or any other. Then we have a sequence like this. 1, 1, 2, 2, 4, 5, 8. And, well, if this sequence is winning, this sequence can be either winning or losing for the player who gets move on this sequence, right? If this sequence is losing, then, well, the first player is winning, right? Because he can just make the move equal to 1. And, well, he wins after it. But if this sequence is winning, if this sequence is, if this sequence is losing, wait, something doesn't work here. If this sequence is losing, then, well, we make a move equal to 1, right? We do x equal to 1 and we win, because this sequence is losing. But what if this sequence is winning? Well, then the second player who makes a move on this sequence, he needs to make some winning move, right? And we know that this winning move is at most a1. So let's say that he makes a move equal to 1 or something else. Our sequence will look like this. But let's notice a thing. Our first player, and we know that this sequence is losing, right? Because the second player was winning here, so now it's losing. But we know that our first player could also make a move in the start, move equal to 2, that could get us to this sequence. So this is called the chocolate theorem. I don't know how this is called in English. But basically, when we make a move here, basically, if move equal to 1 is losing for us, then we have some other move that is winning. So what we have shown is that, well, if our first pile is like greater than 1, then we are winning. Cause, well, we like can make the move that makes the move equal to 1 losing. Right? So, now it's some easy for what we are doing. If our first number is equal to 1, then subtract 1 from all the numbers that are further and check if the first number is now greater than 1. If the first number is now greater than 1, then, well, the player that now has the move wins. Otherwise, may continue the process. So, if we'll delete the numbers that are the same, because they won't change anything, we'll get something like 2, 3, 5, 6, 9. We want to, in this sorted array, we want to find the first number such that, well, all the numbers before it are 1, but all the numbers before it are like, well, this increasing sequence 1, 2, 3, 4, 5. And now if we have 7, then the player who makes the move on this 7 is winning. Right? Because, well, this one will subtract 1, so then we will have something like this. This guy will also need to subtract 1, because it's the only move for him. So, we'll have something like this. This guy will also subtract 1. And this guy will also subtract 1. And this one will also have to subtract 1 because it's the only move for him. And now we see... Oh, I haven't subtract here. So we have like 4, 3, 2. And now we see that we have our first number that is... our minimal number greater than 0. We know that we have it greater than 1. And as we have shown previously, well, the player who now has the move wins. So here Alice have move, here Bob, here Alice... Here Bob, here Alice, and here Bob. So Bob wins in this case. And well, if we are given a sequence like this, right? Well, then the player wins, like, we just need to check the parity of the number of the length, right? So that's basically just it. Yeah. So, sorry that it will be so short today. Wait, I will find this game for you. Chocolate game mathematics. Oh, it's called Chomp. Yeah. So basically, you have it here. Yeah, it's called strategy stealing argument. Yeah, so basically that's just it. Yeah. So, well, thank you for the stream today. Thank you. Oh, 135. Well, we see that the first number such that it like... Well, the first number such that AI is different than I after sorting is 3. So, well, it's on the second position, so it's Bob. If it's on the position that is even, then it's Bob. If it's on the position that is odd, it's Alice. Yeah, you can read about this strategy stealing argument and then think about it yourself. I'm sorry for the stream today being so short. well, I performed very bad, so I don't have anything to say, because, well, I am bad. I'm sorry. I like, yeah, I will, it doesn't matter. I am just bad. Yeah, it's Bob for the 135 that you have given on chat. So thank you for watching the stream. I hope that next time someone better like IGM or something will give those streams to you and they will be much better, more tasks. And see you next time. Yeah, the OBS kinda crashed, but yeah, thanks for watching the stream. Stay tuned for more on the channel, and well, you can read the thing that I shown here. Like, yeah, it's like base. I have learned this on this game. It's like best shown here. That, well, we can always make a move that, yeah. So thank you, and see you next time.